Hello, I'm Dr. David Lupkeman. In this presentation, I'll demonstrate how to use the Modbus protocol to communicate with a power system protection relay. We'll begin with an overview of the relay's communication features and the physical connections required. Then in the first part of the Modbus example, I'll show how to transfer protection metering data to a SCADA application written in Python. Next, we'll explore how to read discrete status points and send binary commands to the relay. If you are not familiar with the Modbus protocol, I recommend watching my earlier video on using Modbus with an electric meter. You can find the link in the video description. The electric power system relay used in this example is designed for feeder protection applications and is commonly installed in distribution substations. Its primary function is to monitor feeder measurements for electrical faults and to control the circuit breaker as necessary. In addition to its protection role, this relay offers several secondary functions. It can serve as a data source for SCADA systems, providing breaker monitoring and power metering data. The relay's front panel typically includes a display, which in this example has been configured to show standard load measurements. It also features programmable front panel buttons that allow operators to trip or close the circuit breaker and to view breaker status directly. The table shown here summarizes the categories of measurements available. This relay is capable of measuring and displaying a wide range of quantities, including RMS bus voltage, RMS line current, three-phase power, and energy consumption. In addition, the relay calculates fundamental voltage and current magnitudes along with their corresponding phase angles. For our introductory example, we'll focus on measurements related to a single-phase load. Microprocessor-based relays include a variety of discrete registers designed to monitor the true-false status of different point types. This table displays a subset of these registers, specifically showing the status of protection functions along with the relay's binary input and output states. Registers highlighted in yellow indicate a status of true, all others have a status of false. The connections to the relay are located at the rear panel as illustrated on the left. The corresponding connection schematic is shown on the right. Supply power is connected to terminals A1 and A2, while the Ethernet communication cable is connected to port 1A. At the bottom, you can see the measurement connection points for phase A, B, and C voltages, as well as for phase A, B, and C currents. Finally, the output 101 connection that we will be using in the example is made between terminals A3 and 4. In this example, I'm using the relay to monitor a single-phase load as shown in the wiring diagram. To achieve this, I only need to connect the phase A voltage and current inputs. For local data access, the meter's front panel display shows voltage, current, power, and other related parameters. But we also want to monitor this data remotely through a SCADA application. In this setup, the remote SCADA is represented by a GUI application I've developed running on a separate computer. To enable this data transfer, we need a machine-to-machine communication protocol that allows these two intelligent devices to exchange information. This is where the Modbus protocol comes into play. In this setup, we're using Modbus over a TCP/IP network connection as shown in the illustration. Here, the relay acts as a data server with its own IP address, while the SCADA system functions as the data client, also with its own IP address. Modbus defines 4 object types, and in this example, we're working with 3 of them. Discrete inputs, binary values 0 or 1 that are read-only, input registers, 16-bit integers representing measurements, also read-only, and coils, binary values 0 or 1 that are both readable and writable. Communication between a client and server uses a straightforward message format that includes a function code to specify the type of transaction. The table shown lists several common function codes used to access discrete inputs, coils, and input registers. In this example, we use Ethernet communication. The client and server are connected through a home network router with the gateway IP address 192.168.0.1. The server is a relay configured with the IP address 192.168.0.30 set in the relay's port configuration. The client is a laptop running a Python SCADA application. Its IP address is 192.168.0.29, which is typically assigned dynamically by the home network when the laptop connects. To check this address, you can use the ipconfig command in a PC terminal window. For Modbus TCP/IP communication, the client monitors port 502, which is the default port for Modbus traffic. This diagram illustrates a Modbus message exchange between the client and server for reading multiple input registers. The client sends a Modbus request with function code 4 starting at register 021C in hexadecimal, which equals 540 in decimal. It requests two registers representing two 16-bit integers that the client will combine into a single 32-bit value. If the server can fulfill the request, it responds with the message using function code 4. The response data also includes the number of bytes returned, 4 bytes in this case, and the register values 0 and 2E7C, both in hexadecimal, which combine to form 11,900 in decimal. Applying a scaling factor of 0.01 at the client gives 119.0, which represents the load voltage in volts. This slide shows a Modbus message using function code 2 to read discrete inputs. The request specifies a starting register of 8 and a quantity of 1 register. If the server successfully processes the request, it responds with function code 2 with data field containing the byte count, which is 1 in this case, the register value 1, indicating a true state. This final transaction slide shows a Modbus message using function code 5 to write to a coil. The request targets starting register 0 and sets the register value to FF00, which means writing a true state to this coil address. If the server successfully processes the request, it responds with function code 5 and a data field containing a padding value of 0 and the register value FF00, confirming the coil was set to true. To enable the relay to communicate using Modbus, we need to enable a few key parameters. For this particular relay, we will use the setup tool to set the IP address for the client or master device to 192.168.0.29 and the port number to 502. To improve the accuracy of this relay's metering measurements, we use its internal math variables. Each math variable consists of both high and low 16-bit registers, providing a total resolution of 32 bits. Scaling factors can also be applied as needed to match specific measurement requirements. In the example shown, refer to the screenshot on the left, we are reading 10 values, including fundamental voltage magnitude, frequency, fundamental current magnitude and angle, RMS current, real reactive and apparent power, power factor, and energy consumption. These math variables are accessible via Modbus Input Registers starting at relative address 540, as shown in the table on the right. In this example, we also read a discrete input register that reflects the status of the circuit breaker as represented by the internal discrete variable 52A. The 52A variable is located at relative address 8, as shown in the table within the setup tool. Instead of using a physical circuit breaker, I've created a simulated breaker using the relay's internal logic gates as illustrated here. To demonstrate a coil write command, we will write to output 101 which is mapped to relative coil address 0. By toggling output 101 using the coil write command, we can observe the change in its state within the relay setup tool. Once the relay is set up, the next step is to configure and start the laptop computer acting as the client. The client SCADA application is written in Python and uses the PyModbus library to send and receive Modbus messages. A graphical user interface, or GUI, is built using the tkinter graphics library. This interface displays the relay's meter values, the closed trip status of the relay's circuit breaker, and includes a coil toggle button for operating the output 101 switch. It also allows us to adjust the Modbus sampling rate. All GUI-related functionality is handled by the meter GUI class, which defines the layout and behavior of the display panels and buttons. The program uses a list structure called channel, which stores the names of the input registers, their corresponding scaling factors, and units used for properly displaying the measured values. To begin reading from the relay, the client connects to the server device at IP address 192.168.0.30. At each sampling interval, the function read input registers retrieves data from the specified start address for the required number of registers. Once the raw 16-bit register values are received, they are combined into 32-bit signed integers using the combine high-low function. These values are then scaled appropriately and displayed on the GUI. The closed trip status of the relay circuit breaker is updated in the GUI using the read discrete inputs function. When the physical trip or close buttons on the relay are pressed, the status change is reflected in real time on the GUI. We can also toggle the output 101 coil register using the Modbus read coils and write coil commands. When toggled, the output 101 status on the relay shows a 1-second pulse, which is visible on the relay configuration program. When the code is running, all measured quantities update in real time based on the configured sampling rate. For example, when a coffee maker is connected as a load, the GUI displays current and power readings for its water heating element. Since the element is resistive, the power factor remains close to 1. The source code for this project is available on the GitHub repository linked in the video description. Now we'll use Wireshark, a network protocol analyzer, to inspect the Modbus TCP/IP communication between the SCADA client on the computer and the relay server. You can download Wireshark using the link provided in the video description. To narrow our focus, we'll apply a Modbus filter, allowing us to see only the TCP/IP traffic that carries Modbus commands. Next, we'll use the dissector view to examine the detailed contents of each Modbus message. By looking at the IP addresses, we can determine which messages are being sent to or from the laptop client. Let's begin by selecting a Modbus message that shows an input register read command sent from the client at address 192.168.0.29 to the server at address 192.168.0.30. Next, we'll drill down into the dissector view located in the lower left corner of the Wireshark interface. As discussed earlier, this message uses function code 4, which is used to request 20 register points starting at relative address 540. Since our SCADA application uses 2 Modbus registers per measurement, we have to request 20 registers to retrieve 10 complete measurement values. Wireshark also highlights the hexadecimal representation of the Modbus message within the TCP/IP packet. You can see this highlighted area in the lower right pane. Lastly, note that the register count value of 14 in hexadecimal is equivalent to 20 in decimal, confirming the number of registers requested. The relay server responds with a message that uses the same function code 4 and returns 40 register values representing the requested data stored in the relay. These values are returned as pairs of high and low unsigned integers. The client still needs to apply a combination algorithm along with any necessary scaling and conversion factors to interpret the data correctly. For example, if we examine the 5th and 6th register values, we see 0007 in hex and D3ED in hex, which equals to 54,253 in decimal. Combining these two gives us a 32-bit value of 513,005 in decimal. When we apply the scaling factor 0.01, this results in a value of 5130.05 milliamps, which corresponds to the load being turned on. The next message type we'll examine is discrete inputs. When the Read Discrete Inputs message is selected, the client sends a Modbus message using function code 2. In this example, the message specifies a starting register address of 8, which corresponds to the 52A status. The register count is set to 1 because we are only requesting a single value. The relay server responds with function code 2, matching the client's request. It returns a byte count of 1 and a value of 0 if 52A, that is the circuit breaker, is open. Alternatively, if 52A is closed, the value returned for 52A is 1. Finally, let's look at the coil write command, which is activated using the toggle coil button on the relay GUI. When the write single coil message is selected, the client sends a Modbus message using function code 5. The message includes a starting register address of 0, which corresponds to output 101, and the value FF00 in hexadecimal, indicating the coil should be set to true. The relay server responds with function code 5, matching the client's request. The response includes data fields with padding and the register value FF00, confirming that the coil was successfully set to true for 1 second. In this presentation, I have shown how the Modbus protocol can be used to enable communications between a SCADA client and a relay acting as a data server. In the first part of the example, meter measurements from the relay were transferred using Modbus Input Registers. Then, discrete true-false status points were pulled by using Modbus Discrete Inputs. Finally, it was shown how SCADA could send on-off commands via Modbus coil commands. Source code for this example can be found at the GitHub site provided in the video description.